Hello, welcome to the Think Onward webinar series. I'm your host, Clark Dever. We're lucky today to be here with Jesse and to learn a little bit more about denoising algorithms for the geofoundational model. So Jesse, I'll let you take it away.
Today, we're going to be talking about denoising with the geophysical foundation model. We're going to talk about some of the kind of cool downstream use cases for the geophysical foundation model. In this case, we're going to be looking at some synthetic data. We're going to talk about the fine-tuned version of the GFM, the geophysical foundation model. We'll talk about this fine-tuned version that we've named denoiser. Really descriptive name, talking about what it does. Denoising, we're going to walk through some high-level overview of how to use it, where to find it, how to get access to it, and get up and running with it. We do have a Hugging Face for this model, so you can download the weights. If you have used the geophysical foundation model in the past, we have a GitHub page for that as well. That holds the architecture. And we'll talk a little bit about some of the very minor, I think it's like maybe 10 lines of code out of the original code base that you have to modify to make the denoiser work, make those weights work with the architecture. So with that, as is kind of standard protocol for data science type work, we've got a requirements.txt file. You can find that in the geophysical foundation model GitHub. That's a great place to get started, build an environment, get rolling with things. The denoiser has the same exact requirements, and so really, really interchangeable there. So to begin with, you're probably wondering, like, where did this come from? You guys just kind of popped out of nowhere with this denoiser geophysical foundation model thing. What is it all about? Where did it come from? So last year, Think Onward, the challenges team ran a challenge focused on denoising Seismic. This was called the Image Impeccable Challenge. And for this challenge, we had a baseline score, and that score was 0.90. And that was our benchmark. So that was what people were trying to get above for the challenge. There's some more information linked in this notebook as well. If you want to go check it out, read up on it, see what people did. And we strongly recommend, for other use cases for denoising, keep training this model, fine-tune it on your own data set. This one was specifically built for the Image Impeccable Challenge. So it has seen the data in that challenge. So that's where this model came from. So now that we kind of know where it came from, what it was built to do, let's kind of recap what downstream tasks are. So a foundation model at the heart of it is just a model that's seen a bunch of different data. In this case, the geophysical foundation model was trained to do interpolation on just a boatload of seismic data. From there, a foundation model can then be used for fine-tuning for additional kind of like other tasks. Think of it as like transfer learning. So in this case, we're just taking our model that has seen a ton of data and we're retraining it to, in this case, denoise seismic, so predicting seismic without noise in it. You could train it to do things like segmentation. So you could train it to pick out different horizons. You could you could fine tune for picking faults out of seismic. So you can train it for kind of all these different downstream tasks in addition to that original interpolation. So with that being said, everything that you need to get started is in here. This tutorial does assume that you have downloaded the Geophysical Foundation Model repository. So that's what this line here is importing it for us. So just make sure you have that from GitHub. There's a full README on GitHub that'll walk you through how to fork it, download it, get it up and running on your own machine so that you can work through it there. This tutorial is just going to assume that you've gotten to that point and you can import our Elastic Bitmate class. So with that, I'll go ahead and run that. It'll go through, get everything imported, and we should be ready to go. So with that, You do need a Hugging Face account to access to the weights for the denoiser. You have to request model access to get the weights. To do all of this, once you've got a Hugging Face account, you've requested model access, you'll need to set up an access token to use the Hugging Face Hub package. You can do this other ways to get the model weights if you want. This is the easiest way, is to set up an access token, and then you can use the Hugging Face Hub package, which is really, really useful for downloading, uploading, interacting with Hugging Face. It's a great place to get started. And so with that, if I run this cell here, it pops up and says, hey, do you want to add a token in here? And I'll say yes. And so I'll hop over to another screen and I'll copy my token and then I'll just paste it in here. And what this does is just authorizing this notebook to access my Hugging Face account, which has different permissions that I can, in this case, download this model because I have access to it. So we'll go ahead and log in there. And so now the cell is done running. So I'm logged in into Hugging Face so I can download, upload, kind of do what I want. All right. So now that we have kind of our standard things out of the way, we've imported some packages, we've got access to Hugging Face. Let's talk a little bit more about kind of some concepts for fine tuning. So, as I mentioned earlier, it's really good to fine tune your own model from the geophysical foundation model. If you want to do downstream tasks like segmentation, where you're segmenting out those different layers, you're segmenting out different faults versus not faults, or geobodies, or what have you, you'll need to do some fine tune training on the geophysical foundation model. So here's what we recommend. So you'll need to build some kind of a paired data set so you can do that supervised learning. In our case, for denoising, you'll need to build a paired data set with noise and denoised examples. And so in this case, we have our target data set and our basically our noisy data set and our denoised data set. So the model can learn what noise looks like. In this case, you can check out the Image Impeccable challenge that we ran here at Think Onward. If you're like, that's cool, I don't really care, I just want to see the data, we've got some great links where you can download the data, check it out on the forum, get access to that data, and fine tune your own model if you want. All right, so you've got a data set. Next thing you need to do is you need to figure out a way, okay, I've got this foundation model. I need to figure out how good or bad it's doing. So you'll need to build a way to evaluate your model, track its loss, see how it's doing as you go through this fine-tuning training process. This is kind of dealer's choice, depends on if you're doing like a classification or a regression type problem. So if you're doing a segmentation, which would be like classification, or if you're doing denoising, which is more like a regression type task, you'll need to think about what loss you want to use and how you're going to track it through training. The next bit is you'll need to pick which layers you want to freeze and which ones you will want to train during the fine tuning process. So this example that I've got in here is, in this case, we're basically going through setting all of our layers to non-trainable. And then we go through and kind of pick and choose what we want to train during the training process. So we're not retraining the whole system from scratch or building from scratch on top of the GFM. We're just kind of picking the areas that we want to continue training for that fine tuning. This allows it to go faster, train a little bit faster, and train for these specific tasks. This is kind of the cool thing of transfer learning, is you have kind of you've got the backbone there, but you're just kind of adding on these cool little I want to say bells and whistles, but other cool parts onto the backbone. So this is a great example. This is in the notebook. If you want to start, using this to think about, okay, how do I go about picking which parts of the model I want to fine tune, which part do I not want to fine tune, what do I want to freeze, what do I want to make trainable. So this is a great resource to start with. All right, the next thing. So you've got your data set. You've figured out what you want to train on. Figured out how you want to train your model. The next thing is you're going to need a custom data set data loader. Again, I'm going to send you back to the Image Impackable starter notebook. We have so much cool stuff in there. It's on the Think Onward Challenges GitHub page. And there's some really useful things in there, like a data loader that is built for seismic data. It just goes through, loads data, slices and dices it up in different ways so that you can effectively, easily train vision transformers on these 3D cubes. So this is another thing that you might build out. You might grab what we've got in that starter notebook. It's up to you. Kind of choose your own adventure here. And then the last thing that you'll need is to check and see that your model's improving over time. So you've got your data set, you've got your loss set up, you've figured out what you want to train, you've got your data loader set. Now you just need a way to track and make sure that it is learning, that your loss is improving over time, and that your model is learning how to do stuff, that it's learning these different tasks. So with that, that's kind of the general setup for fine tuning. For this tutorial, we're not going to walk through and say, okay, here's how you fine tune your model. Here's how you do kind of this cool cook boogies type stuff. We're just going to jump straight into a fine tuned model that we have, our denoiser model, and what it looks like, how to use it, how to run inference with it, and some of the results that come out of it. We strongly recommend that if you want to use this, do additional training on it, get it to a place where it's working better with your data set. Again, this was trained on synthetic data for the Image Impeccable Challenge, so it does really well with that data set. So with that, we'll move on down to kind of I want to call this like the key changes that we're doing in the model architecture. So if you think back to, I think it was January, we ran our GFM webinar on interpolation. And for that task, the model was tasked with just fill in the blank, or like Pictionary, I guess is another good way to think of it. So we were masking out verticals, slices of seismic, and then saying, okay, model, fill in the blank, interpolate in between these missing, or interpolate over this missing area. So that's the original task. So now we want to fine tune for another task. So in the original task, the first thing we did was we randomly masked traces. So those vertical slices out of our seismic, we'd go through, blank them out, and say fill in the blank. So if you look at the forward encoder from the original GFM, we have this random masking section in here. And so this was where we went through, masked randomly, and said fill in the blank, and rebuilt it over time that way. So since we're not asking it to fill in the blank, we don't need to have this index shuffle or this length keep, which basically help us deconstruct and reconstruct the image. So in this case, for the denoiser, we can just like chunk them out the window, get rid of them. We don't need them. And so you'll see down here, this is what our new forward encoder is going to look like. We just got rid of that chunk where we're going through and masking out our traces. And again, since we no longer need to take our index shuffle or our length keep, we can get rid of that out of our method in the class. So this is our new denoiser forward encoder method. Our next thing to think about. So we messed with our forward encoder. Okay, so now we've updated our encoder on how we're going to encode our images. Now we need to change up our decoder. So again, we're not trying to fill in the blank. We're not trying to interpolate. And if we look at our forward decoder from our original GFM, we had shuffling and image restoration for masking. So we have our IDs restore in here. And so we're not doing that anymore. So we can get rid of our IDs restore, And we're actually going to change this chunk kind of down through here. And ultimately, what we're going to do, let's see if this will all fit on one screen. I don't think it's going to. But we're effectively going to set this parameter to our ID's restore shape is going to be 160. That is the width of our image that we're going to feed in or take out of our decoder. So we're just going to set this to 160. You can see that we've updated it to 160 here. And since we no longer have our ID restore, we can just get rid of that. And this is our updated decoder. We're just setting this to the width of our image. All right, so far we have changed our encoder a little bit because we're no longer masking and interpolating. We've changed our decoder because we're also no longer masking and interpolating, and we have a set width of our image. So then that means that our last bit, our forward method, needs to get updated. So if we look at our original forward method here, we took in our image, we took in our index shuffle, our length keep. Well, we're not using these two things anymore, so we could probably get rid of them. So in this case, we'll just get rid of our index shuffle, our length, and our length keep because those are going into our forward encoder. So now our new forward method is really nice and happy, easy to use. Just takes our image, we encode our image into our latent space, and then our decoder takes our latent space and returns our prediction. So those are the main changes that we're going to make. So it's just 3 changes. If you pull this off of GitHub, you can literally just copy and paste this into the GFM code. So you're probably saying, what GFM code? So this is our GFM code in our elastic vitme Python file. And in here, we can scroll down. We see our patch embed. We see our custom head. And then we have our elastic vitme class in here. And so this is where we're going to update those methods. So if we scroll down a little bit further, somewhere in here. So there's our forward encoder. So we would just update this here, update our forward decoder, and then update our forward pass. So this is just for inference. So for inference, we can just update these. If you're going to do training, you're probably going to want to update your forward pass with the loss function and make sure that you have a way to track your loss as you go through training. All right, so we've gone through, we have our data set, we've got our model, we've updated our architecture, we have our paired data set, we're ready to rock and roll. And so now, oh yeah, we logged into HuggingFace. We have access to the model. Okay, cool. So what we need to do next? Well, first we need to get access to the model. So we need to get that on our machine. We're logged into HuggingFace. So I'm going to go ahead and run this cell here. And what this does is going to download our denoiser weights to this local directory called denoiser weights. And if I come over here on the left-hand side, I can see our file here. I downloaded it a couple hours ago because I didn't want to sit here and wait for it to download. So we can see, we open it up. We've got our safe tensors, our .bin file, our config. So this is our denoiser files from HuggingFace. So if I jump over to HuggingFace here, you can see on HuggingFace that this is our denoiser repository. We've got this nice README in here that's got information on how to use it. And if I click on files and versions here, remember HuggingFace is just a fancy Git repository. If I click on files and versions, we see our README, our config, our bin file, and our safe tensors file in here. So we've got all our files here that matches what we've downloaded. Cool. So we've got a couple gigs of weights. We're ready to get started with our denoising task. Almost. We've got our model. Now, once we've got our weights downloaded here, we've confirmed that they're on the left-hand side here. They're all downloaded. What we want to do is we want to first set our device. So we've got a CUDA device on this machine because GPUs are awesome. And then we're going to create an instance of our Elastic bitmap class here. And then we're going to load it from our pre-trained weights that we downloaded in denoiser weights here. Set it to float, send it to our CUDA device. So let's jump in here. So we've got our everything loaded onto our CUDA device here. We can read through here and say, yep, everything loaded from our local directory here. If you want to, you can go through, double check that everything looks good, but we didn't have any complaints. So we've now got our model loaded up into this variable called denoiser. It's this instance of our Elastic bitmap model. So cool, we've got that loaded up. So let's recap from the top, just because I always like walking through this. We have our data set that we talked about. Have we loaded that? No, we've not loaded that. We have our model. We just loaded that. We're good to go. So the next thing we need to do is load up a data set, see how the model does. And so in this case, I really like the image impeccable data set. I think it is one of the coolest little data sets that, well, not little, but pretty good sized data sets that we've put out. It's got this nice paired noisy seismic and kind of like clean, original, unnoised, denoised seismic. And so in this case, I've pulled in one volume here, this NumPy volume. And what we'll do is we'll pull in this, load it up, and then just look at it. If you know anything about me, I love data viz. It explains a lot of stuff. It makes it so much easier to work with data, is just looking at it, seeing what's going on. So in this case, we'll just load it up to this seismic volume variable, and then we'll go through and use this visualize seismic function to just look at it, see what it looks like. We've got some inlines, cross lines, and a time slice that we'll look at, and we can change these parameters as needed. So if we run that and then run this next cell that has actually runs our volume with our inline, our cross line, and our time slice, we can look at our data set. So here we have our inline. This is inline number 80. We've got our cross line number 200. We've got our time slice, and all these red dashes kind of show, like, kind of orient you in the space. So here's inline 80, which would be this red line here. And I've got cross line 200, which is this line kind of across here. And then on both our inline and cross line, we have our time slice at about time 250 here. So that kind of gets you oriented in what we're looking at here. So like a vertical slice, and then our kind of like horizontal cross slice, time slice through there. And if we look at it, it's kind of hard to see on the inline and cross line, but you can see kind of just a little bit of really soft noise in there. It's kind of small. We look at our time slice, you can actually see some really nice noise in there. These kind of really small things. It's like if you dropped a pebble into water, into like a pond, and it was not frozen, and you're looking at it from above, you can see all the ripples kind of going out there in this time slice. So this is a really shallow time slice. We could go up higher. We could make it like 150 and look at it, and it's not super interesting because we're just barely touching what would be the bottom of the sea floor here. If we go down a little bit somewhere more interesting, like 650, you can see here at about 650-ish, we have this little salt diapir thing going on. We've got maybe a fault cutting across here. If we look at that, we can see our salt diapir here, which is this kind of funky looking thing. And we can see a very faint fault in here. Now we can really see this noise cutting across through here. Again, looking like we dropped that big honking rock in the pond now. We've got all these waves coming off of it here. So that's kind of our noise that we're looking at. If we want to change, let's go to like in line of 10. We can kind of poke over to the left here, see what we've got. And we can look at our noise down low, up high. You can see we've got some noise up here too. So generally we've got, kind of noise all over the place. Let's go to, I think that'll go to 300. Not, let's go to 250. So you can kind of slice it and dice it however you want, and look at it in different ways and get a feel for what this data set looks like. So now that we kind of understand, okay, this is what it's going to look like. Here's where all of our noise is going to be. Now we get the fun part. We've got our model loaded. We have our data loaded. We've looked at it, said, okay, let's see what we can do. Now we're going to run through and do some predictions. So we've got this really handy dandy function here that'll actually run through an entire data set. So if I had more than one volume in here, it would actually go through, grab all of the seismic volumes and run through and basically denoise them all at once with the model. So it goes through, loads up the data set, does some standardization by rescaling from 0 to 255. And then in this inner for loop here, ultimately it's just resizing. So it's going through, taking a slice of our seismic data, resizing it, sending it to our CUDA device, which is all of that, sending it to our CUDA device, running our denoiser on it, scaling it back, taking it off of our CUDA device, rescaling it back to our original size, and then adding it in to a seismic volume, or like predicted seismic volume or clean seismic volume. So that's what this whole next cell does, is it just iteratively goes through chunk by chunk by chunk, and denoises each one. So if we run this, it'll go through, tell us that it's started running. And one thing to keep in mind is that this is going slice by slice by slice in one direction. So think of it as like kind of going left to right through the seismic volume, or right to left in one direction. It's not doing everything in 3D. So just keep that in mind. This is a 2D vision transformer. And so that's done running. And now we can do some QC and see what it looks like. So this is our quote unquote like cleaned up, denoised volume. And we can see that, yeah, it looks a little bit cleaner. We still do see some kind of very faint noise in here. The cross line looks pretty similar. The inline, you might notice that we see these kind of vertical, I don't know, like a barcode kind of thing going on. And this is due to the fact that we are looking at things as 2D slices. So in this case, we're looking at each cross line, denoising it, and then like think of it like we're going through a deck of cards. We pull the card off, denoise it, put it down. Pull the next one up, denoise it, put it down. And so we do see that we do get some changes in our original values. And that's where these kind of like vertical stripes are coming from. But if we come back up and look at our original noisy seismic volume here, you can see we've got a lot of noise in here, kind of right off of this fault. You can see that it's doing pretty good with the higher amplitude, the larger noise, and kind of having a little bit harder time with this really more subtle stuff that even as a human, you kind of look at it and go, yeah, that's kind of tough. That would be really tough to remove. But it's doing a good first pass at this. So that's kind of the fast and easy way to get running with the denoiser. If you really want to double check and see what the original seismic looks like, you can also load that up and say, wow, look at how nice and clean this is. There's not a trace of noise in this data set. So you can see where there's area areas where there's definitely room for improvement for the model. Maybe it's additional training time, maybe it's additional training data, maybe it's throwing more synthetic data at it. There could be a variety of different ways to continue fine tuning the denoiser for getting from this kind of like very subtle little bits of noise left to this nice, very clean original seismic with no noise in it whatsoever. So with that, I will also highly recommend we have the Image Impeccable winning solutions are on GitHub. If you go to the Think Onward GitHub challenges repository, all of the winning solutions for denoising are on there. Check them out. Lots of really cool units on there for denoising that have some really, really interesting results that did really well. You might think about, okay, how can we integrate what we've learned from the geophysical foundation model, the denoiser, with these units? Is there some additional, maybe you build kind of a new interesting decoder off of the GFM to complete this task? It's kind of, I will leave it up to you all. But that's kind of the high level run through of the denoiser. I'll go through one quick summary of what we did. So we got the GFM code on our machine. We got it up and running with a requirements.txt, installed all of the things we needed to run it. We had our HuggingFace account. We got logged in. We got ready to download the model weights and made sure that we had access to them. We thought about fine tuning, what you might need to do in the future. We made our changes in our architecture for the GFM. So we just got rid of that fill in the blank type architecture for our forward encoder, our forward decoder, and then our forward pass, our forward method here. Once we did that, we were good to go. We loaded the fine-tune model. So we downloaded it from HuggingFace to our local machine. Once it was downloaded, we then loaded it up into a new instance named denoiser. So this is our Elastic Bitmay instance. We loaded up our pre-trained fine-tuned model into that instance and then sent it to our CUDA device. Now that we had our model kind of over in CUDA land ready to rock and roll, we had our data set, we looked at it, said, yeah, it's pretty noisy, could use some denoising. We went through, loaded that model up, ran through slice by slice by slice like a deck of cards, made our predictions on each slice to denoise. And remember, we're predicting our clean seismic from our noisy seismic. Went slice by slice by slice. And then we visualized to see, yeah, there's some areas for improvement. And then we compared it with our cleaned up version to say, how does it look? Could we do better? Could we do worse? We could probably do worse. And so this is a great jumping off point for you to start thinking about, okay, what other cool things can we add in here? Is there additional training? Is there additional data that it can see? And really, kind of take this and run with it and see what you can do with it. With that, are there any questions, comments, thoughts, concerns?
I'm gonna ask you my normal question, which is, what was the interesting thing you learned during this, building this process? Was there any kind of unexpected moments?
I think one of the most interesting things that came out of this is like, the different approaches to it is, do you build a model to predict the full seismic, like this cleaned up version, or do you build a model to predict the noise? Like it's easier to predict just the noise, or do you like make the whole seismic without the noise? It's like I don't know I don't have a good like cats and dogs pictures analogy for it, but it's That's something that people might think about is like it might be easier to just predict the noise rather than to predict the full seismic without the noise in it.
What do you think some of the weaknesses are in this approach?
Oh, yeah. So definitely, it's fully trained on the image impeccable data set, which is 100% synthetic. So that is definitely a hard part for it. Is it needs to see some, I want to call it like hand denoised, or like things that people have denoised with their own like inversion models, that sorts of stuff would be really beneficial, just so that it can kind of start to close that synthetic to real gap would be really nice. So additional training would be great for it. Um, I think that's kind of the big stuff, is like really just additional training, additional time, additional data, and for people to kind of dig into it a little bit further.
No questions in the Q&A, so I guess we'll call it a day. Thank you, Jesse. Thank you to the audience, and we appreciate you all joining us today, and we hope you learned something new.